So what we talked about last class, 3.1, extrema, the extreme value theorem, finding those highs and lows, right? And so the max or min, or we call them extrema. Sometimes they are called critical values. These are all places where the derivative of a function equals 0 or the derivative of a function does not exist. Critical values, places where you have, right, peaks and valleys, right, highs and lows. Here is a critical value, here is a critical value. Sometimes you can have a critical value that looks like this, where the derivative does not exist, or it's a sharp curve, or you have like an absolute value function here. Here the derivative is 0. Here the derivative is 0. So those were our mean, our extreme value theorems. And we're looking for these places in a particular function on some range from A to B. On some range from A to B. In A to B is the idea. So the homework we had last class was about this, finding those extremes. You also had to test the endpoints to see which is the highest and lowest. To see the max, highest, and lowest. Because you don't know, maybe the endpoint is the highest spot. Maybe there's a peak here, but it's not the highest point. It ends up over there because these graphs can continue on going up forever. Maybe the highest point or lowest point is on the end. So you got to check the endpoints as well. So our homework was page, I said 171. Numbers, what did I say? 17 to 31. 17 to 31 odd, I think is what I said. Yeah. So which of those questions would you like me to review? I got number 19. Okay, 19. Any other ones in that list? Look through those. See what you want me to go over for you. 29, 31, 21, 23. Oh boy. Oh boy. Let's see. All right. Of the choices here, let's look at this. 19. 19 looks complicated. Let's try that one. 39. Okay, those are bonus questions. 39, 33. 33, 39 were extra. These were bonus. There's probably not time for those, but 33, 39. Yeah, maybe not time for those. We'll find out. 23. We can do 23. That's pretty easy. 21, sine x and cos x. And then we had 29 and 31. 29 and 31. Man, these are all really good questions to go over. 21 is useful because it's got the sine and cosine. How do we solve that? 31 is good. All right, I'll do 30. I'm going to skip 29. I'm going to try to do these 4. We'll see how much we can get through. I'm going to go fast, so again, you got this recording, so keep up. 19. We're looking for the critical values. Find critical values. 19, I've got the equation t root 4 minus t. That's f of x. And it's only where t is less than 3. So if we graph this equation, it's going to look, well, I don't really know. 4 minus t, something like this, maybe? From 3 backwards. Maybe it doesn't exist at 3. Maybe this is a 4, goes to 3. I don't know. Looks something, it's got some backwards going direction, and the equations are only everywhere back from 3. So we're looking for all the critical values of the function everywhere less than 3. So we're going to find our critical values, means we're going to take our derivative, dd, in this case t, because t is like x in this situation. So we're just going to take the derivative of this equation, find our critical values, and then set that derivative equal to 0, right? Where the derivative is 0 or does not exist. So how do I do the derivative of this complicated looking? I got a t here, I've got a radical here. How do I find the derivative of this? Well, these are being multiplied together. So I've got an f and I've got a g. So I use my product rule. First times derivative of the second plus the second times derivative of the first. I have two functions. I've got to use my product rule. That should be, embed that in your brain. F and g. So first times the derivative of the second. The derivative of square root 4 minus t. Well, this is 4 minus t to the 1/2. So I know it's going to be 1 over 2 radical 4 minus t. But then I need to do one more thing and take the derivative of my inner function. This is my inside function. And so I need to do a chain rule here. Derivative of the outside times derivative of the inside. And the derivative of this inside part here is negative 1. Because my negative t here, so this means this is going to be negative 1 over 2 root 4 minus t. I've got my inside part, I have to do my derivative of the inside. This is a chain rule problem. Whenever you see things that have like square roots like that, or you know, trig functions with like a cosine of some equation in here, you know you have to do some chain rule. You know you have to do the derivative of the inside too. Always look for your insides. So that's the first times derivative of the second. First times derivative of the second. Plus second times derivative of the first. Well, the second is just radical 4 minus t. Derivative of t is a 1. So that's pretty good there. Cleaning this up a little bit, I'm going to have negative t over 2 radical 4 minus t plus radical 4 minus t. Okay. And I want to make this equal to 0. Oof. Equal to 0. So I want to find some places where we can get this equal to 0. How can I, or does not exist, or does not exist. The other thing. Oh, 3 would be over here. What am I doing with negative? Bad graph, everyone. What did I even do? 3 is over here. 1, 2, 3. So it's like this. Something like this. Maybe 4 is here, and it's like, maybe it goes to 4, but we're ignoring all this. Only 3 and backwards. Okay, so looking at this equation, how can we find out where this is equal to 0? Solving this complicated looking radical equation, what kind of algebraic manipulation could we possibly do to this situation here? What are some solving methods we could do? What are some steps we could take to get this solved? Any ideas, everybody? Minus the square root? Yeah, move this square root over, right? I got this piece here, move it over to the other side, right? Just set that over. Or I could take this piece, move it over, either way. But yeah, let's minus this square root piece over here, move it over to the other side, do some algebra manipulation. I've got negative, oopsies. got negative t over 2 radical 4 minus t equals negative radical 4 minus t. And since they're both negative, I'm just going to cancel the negatives on both sides. Yeah, since I have, this was negative here, this was negative here, if they're both negative on both sides, I can just divide by -1, cancel the negative on both sides. I just want to do that, make my life easier, make them positive. Now I've got this situation here. What I can do is, imagine this is over 1, cross multiply. Helpful strategy, being able to cross multiply. And a really nice thing about doing it this way is that I have a radical times a radical, the same things, and that radical is going to cancel out. That radical is going to cancel out. So that's going to be really, really nice to make my life easier. So I've got t, right? T times 1 is t, equals 2 times radical 4t, 4 minus t times radical 4 minus t is just 4 minus t. So distribute this, 2 inside, I've got t equals, now we have an easy problem, 8 minus 2t, add the 2t on both sides, add the 2t on both sides. I'm going to have 3t equals 8, so t equals 8/3. That is one of my critical values, the place where the equation is going to equal 0, 8/3. Okay? So I solved this equation. How do we know, here's a question someone asked, how do we know if it's appropriate to cross multiply? You cross multiply, whenever, cross mult, whenever you have something over something equals something over something else. Whenever you have two fractions equal to each other, or even if you have one's a fraction, one's not. Or, because you can always make this a fraction. Or even if you have one's a fraction and one's like a 1 over something. But it cannot be like adding together. It has to be just pure, like one big fraction equals another big fraction. So when you have two fractions equal to each other, or there's like just, you know, no adding, no subtracting, no other craziness, just big fraction equals big fraction. That's when you can know you can cross multiply, whenever this situation is in the world. C over d, fraction equals fraction. Two fractions equal to each other. All right, so we got 8 over 3. Let's just make sure that this is in our range. T has to be less than 3. Is this less than 3? Plug it into a calculator, we get about 2.66 repeating. So yeah, we're okay. We're in our range. So there's my critical value. Any other critical values in this equation? Any other critical values in this equation? One critical value where we found where it was equal to 0. We solved all the situation where it was equal to 0. Any other little detail in this equation that gives us a hint that there might be another critical value somehow in this equation? Ayala, welcome. What were some of the reasons we might have a critical value, right? We set it equal to 0. We set it equal to 0. We solved our equation, rearranged, did some cross multiplying. What's another reason we could have a critical value? We got it equal 0. Our other potential reason for a critical value is when it's a DNE, when it does not exist, right? And there are a few cases, a few situations where things won't exist, right? What are some causes of things not existing? when you divide by 0 on the bottom, right? When you divide by 0, that might be a cause of D and E. Or if you try to take the square root of a negative number, that might cause a does not exist, right? Or what are some other ones? I think these are the two main ones that you'll see. Dividing by 0 and doing a square root of a negative. So we have this square root we got to be careful of. We don't want to have a negative here. So as long as my t value is bigger than 4, right? Or is this less than 4? Less than 4. As long as the t value is less than 4, then we'll be okay. So remember how we test for D and E's? We say, okay, this value here, to exist, 4 minus t has to be greater than 0. Every square root has a little square root test. Test for things that don't exist for a square root. The inside of the square root has to be greater than 0. And so we take that and we kind of like do a little test over here. We say, okay, if this is true, what has to be my situation? If I add t here, add t, I'm going to get that 4 has to be greater than t. Or if you flip it around, we say that t has to be less than 4. And that's okay because our limit here was that t was less than 3. So that's okay. So no problem about t values being less than 4 because all the values are less than 3. So that's going to be definitely less than 4. No problem there. The other potential problem is down here. I have a denominator variable. And I could figure out, well, is there a situation where my denominator could equal 0? What is that possibility where my denominator could equal 0? My two different tests, right? I have to test for the square roots. I have to test my denominator being 0. What value would make this denominator 0? Well, again, if I rearrange this, basically this inside square root has to be 0. So if t equals 4, my denominator would be 0. Is this value t equals 4, is this allowed in our equation? No, it has to be less than 3. 4 is not less than 3, right? T has to be less than 3. So because of this, we say this is not allowed. No problem here. Or I should say not allowed. Not in the range, in the domain. So I don't need to worry about t being 4. I don't need to worry about this denominator being 4 because it's not part of my answer. It's not going to be part of the solution. We have all the values less than 3. But good to be aware of it. It's important to be aware of that situation just in case I need to worry about that type of situation, that type of value. My denominator is 0. I got to check, well, what would make this bottom part 0? A 4 would make the bottom 0. Is 4 allowed? Nope, 4 is not allowed. So I don't need to worry about it. I can set it out of my mind. Same thing with the radical restrictions. T has to be less than 4. Is t going to be less than 4? Yeah, t is going to be less than 3, in fact. So it's always going to be okay. So the only critical value here is the one we solved for, 8 over 3. 2.6 is less than 3, so we're good in that direction. And we found the one critical value that our function is going to have. Questions about that? Again, you're checking your domain. Check all the values to see what's going to be okay. All right, that was 19. Again, I'm going to burn through these. What else did I say? 21. Oh, right, radicals. I mean, trig functions. Okay, 21. 21. Again, finding the critical values, I've got sine squared of x plus cosine of x, oopsies, cosine of x, where x is between 0 and 2 pi. So one cycle of my unit circle, one cycle around the circle, 0 to 2 pi, right? So I want to find my critical values. My critical values are the places where the derivative is equal to 0. So do my derivative of this problem, set it equal to 0, see what I can solve. So, derivative of this. Derivative of sine squared. So I use my power rule and my chain rule. It's going to be 2 sine x. So that's the derivative of the outside, right? Take the 2, bring it in front. Take the 2, bring it in front. Don't change the sign yet, because this is, remember, sine squared is the same thing as saying the sine of x squared. So do my chain rule. Derivative of the outside, the squared part first. Bring the 2 in front, leave the sign alone. Times the derivative of the inside. Derivative of sine is cosine. So 2 sine x cos x is the derivative of sine squared. Plus, derivative of cosine is, well, negative sine. So this is going to be minus sine of x. And I want to set this equal to 0. So we have our function. This is f of x, our function. I want to find the critical values, find the critical values of this function. So to find the critical values, they're the places where the derivative equals 0 or does not exist. So we took the derivative, got the derivative, did our derivative of sine squared, used our chain rule, put the 2 in front, 2 sine x, derivative of the outside part, 2 times, don't change the inside, right? Chain rule says do the outside times the inside, derivative of the outside times the inside, derivative of the outside times the inside, times the derivative of the inside part times the derivative of sine is cosine. And then the derivative of cosine is negative sine. Solving this, we have this equal to 0. We see we have this complicated thing. I don't want to make this like, I don't want to move this sign over here and have it equal and then maybe like divide a sign. It's going to like cause a bunch of problems. When you have sines and cosines in situations like this, what you really want to do is see if you can factor them out. Start to factor them out. And I can take out the sine from both of these. So I'm going to factor out the sine. You want to factor, let me do it up here. Factor out the sine. Factor with trig equations. Instead of solving like a normal one, trig problems you really generally want to factor. So we're going to get sine times 2 cosine minus 1. And then we have our zero product property, where we have two answers, right? We have the sine equals 0, or 2 cosine minus 1 equals 0. Right, we have like this equation times this equation. This is like A times B. And the zero product property said if you'd have two multiplications, break it apart into two answers, two potential answers. And this is why we want to factor with sine and cosine, because you get all the different possibilities. All right, so let's look at our unit circle. Oh God, trigonometry, everybody. Unit circles. Where is the sine equal to 0? Where is the sine equal to 0? Pi, yep, that's one answer. Where else is the sine 0, right? Sine is the y direction. And 2 pi or 0, right? For sure. So x could be 0 and pi, where the sign is 0, right? Sign is the y direction. And if we're going up and down, we have no up and downs on those two locations. So that one's done. Got those critical values here, 0 and pi. This one I have to solve. Add 1 to both sides. You see it's probably going to be 1/2 here. 2 cosine x equals 1 divided by 2. I get that the cosine of x is 1/2. And again, your unit circle, where's the cosine 1/2? Cosine is my x direction. 1/2 is the small side, right? So I've got this angle here, and 1/2 here, this angle down here. Here are my two locations where the cosine is 1/2. And very good, Perry. So yes, this is pi over 3. Your upper angle, right? Your higher angle, right? The down here angle, this is pi over 6, right? Lower angle, pi over 6. Upper angle, pi over 3. And then you have 1 pi over 3, 2 pi over 3, 3 pi over 4, pi over 3, 5 pi over 3. So we have x equals pi over 3 and 5 pi over 3. So there are all of our critical values for that equation. All the places where this equation either peaks or has a valley, a max or a min. Again, this is where the cosine is 1/2. Cosine is the x direction, and the sine is the y direction, where sine equals 0 here, and sine equals 0 here. And here this 1/2, here's where the cosine equals 1/2. Right, positive 1/2, we're going in the positive direction, and so we have the two possible angles for our cosine here and here. Cosine, right? We don't really care about the sine being positive or negative, right? The cosine, as long as this is 1/2. Cosine is 1/2 in this spot right up here, and the cosine is 1/2 in this spot down there. Again, remembering our unit circle. It's been so long. All right, so that's how you solve these sine cosine things, memorizing your unit circle. I said 23 I wanted to do, and then 31. Right? 23, 31? 23 and 31. Yeah, let's do this. I zoomed in on my note here. 23. This one should be fast. This one we're actually finding the extrema. Find extrema, because we're told a range. We're told a range of values, so we're actually finding the max and the min. My function, it says, is 3 minus x, and the range, it says, is between -1 and 2. So, find the extrema. The way we did this was the same. We start this problem the same way we started the other problems. We find the critical values. So steps, again, the steps. Find critical values. And to find the critical values, we set the derivative equal to 0. So let's do the derivative here. And I'm going to know that the derivative f prime, the derivative of this is -1. So I want to set that equal to 0. Huh? Have I done something wrong? Did I do something wrong here? That's my derivative, right? Look, my derivative. There's my derivative. Okay, you're right. Negative x just says -1. That's my derivative. 3 disappears, right? Did nothing wrong. But like, how can it be equal to 0? I can't. There's nothing to solve here. There's no work to do. There's nothing to do here. Did I do something wrong? That might be what comes to your mind. And the answer is no. You have done nothing wrong. This is exactly the situation that we're in. Because when we did the derivative of this linear equation, This is a line, everybody. Are there any peaks or valleys for a line? No. Yeah, there's not going to be any critical values. There's no extrema. No critical values for a line. There's nowhere where you're going to have the derivative of a line equal to 0, unless your slope of the whole thing is 0, but any line is going to have a derivative, like a constant, some number for its derivative. There's never going to be a 0. That's okay. No critical values for a line. That means our job is even easier. When I set up my grid, plug into the chart, right? When I set up my chart, I have my -1 endpoint, I have my 2 endpoint, and that's it. Those are the only values I need to find. My left end and my right end. I've got no critical values, so I know that like the max and the min have to be on the endpoints, because this is a linear equation. It's just going straight. Well, straight this way down, but you get the idea. My max and min, one of these is going to be my max, one of these is my min. So let's plug them in, try to figure it out. -1, 3 minus -1, that's going to be 4. 2, 3 minus 2, that's going to be 1. Okay, max and min. Done. And it makes sense. The left side's the max, because if we look at this graph, 3 minus x, look at this graph over here, it's going to look like 1, 2, 3. Going to look like this. Well, going to look like this. Right, from -1 up to 4 and over to 2 where it's at 1. There's my graph, right? That's my linear equation. So yeah, of course, the max is going to be the endpoint over here. Max is this one, min is this one, because it's just straight. There's no peaks or valleys because it's a linear equation. So it's helpful to like be aware, right? Try to maintain your situational awareness. Maintain situational awareness. Figure out what kind of equation you're dealing with, what kind of situation you're in. Does it make sense? The answer you have, does it fit with what you understand about the situation? Try to maintain your situational awareness. All right, last one. 31. Again, find the extrema. My function, 6x squared over x minus 2, and my range is between -1 to 5. So I want to find the extrema here, find the extreme values, and so I need to find my critical values. Find the critical values that are within this range of -1 to 5. Find critical values by finding the derivative. So f prime, the derivative of this, okay, well, how am I going to do this? I have a bottom part, a top part. Clearly, I've got to use my quotient rule, right? I have two functions, a top and a bottom equation. I've got my quotient rule. It's the only way I can do this derivative using this quotient rule. So low d high minus high d low over low squared. Low d high, low. Derivative of the high part. Power rule, bring the 2 down in front, that's 12, 12x. Low d high. Minus high d low. 6x squared. Derivative of this bottom part is a 1. Well, that's very nice. Over low squared. Low d high minus high d low over low squared. And I want to set this derivative equal to 0 to find the critical values. Find the critical values. So I've got to solve this where it's equal to 0. That just means I'm doing algebra. So I have to take this top part and do a bunch of simplifying. Let's see. Well, I can take this 12x and multiply it by everything, right? Distribute that 12x. And then this 6x times 1, that's fine. So this is going to be 12x squared minus 24x minus 6x squared over x minus 2 squared. That's fine. Let's see, a little bit more cleaning up. I've got this 12x squared and this 6x squared I can combine. So that's 6x squared minus 24x over x minus 2 squared. Squared. Oh, Rowan. Everything's fine, buddy. I don't know if you can hear his yelling in the background. The dulcet tones of an upset baby. Equals 0. Okay. We're doing okay here so far. Now, what are we going to do? Again, I want to solve this equation. What can I do? I got a top part here. Maybe I could do some factoring. 6 and 24 can divide each other. I've got x's here. He's having a hard time existing. Yes, it's very true. So what do I do? But how do I get, like, what's the next step in this situation here where I can solve? Where do I go from here? I've got this top part, I got this bottom part equal to 0. How do I get these x's alone? How do I solve this? How do I deal with this situation? You're going to end up in these situations where you have a fraction equal to 0. How do we get, what is the answer? Yeah, let's go with that. Sure, Jessica. What do you think we do, everybody? Ideas? I'm asking because you're going to face these situations in the future, and so you're going to know what to do. How do I... that's a good idea, Perry. So multiply by the denominator, right? Yeah, same thing we did last time, right? Remember when we cross-multiplied? It's the same kind of idea. I want to get all my x's on the same level. I don't want to have a denominator. So if I multiply by this thing here, yeah, 0 over 1, right? Same idea. The only thing I care about, whenever I have, here's another little fraction hint. Whenever I have a over b equals 0, I can basically ignore the b and make it a equals 0. Because that is the only way, right? The only way that I have a fraction equal to 0 is if the top of the fraction is 0. That's the only thing that matters. Only the top of the fraction is going to equal 0. That's the only part that really matters when you have a fraction equal to a 0. Because the bottom part doesn't matter. If the bottom part's infinite, it doesn't, it's not going to, unless it's infinity or whatever, but that's a whole other situation. No, the only thing that matters is the top part of the fraction. So you can kind of imagine that this cancels out, and I've got 6x squared minus 24x equals 0. And now that's something I can solve. So whenever you have a fraction equal to 0, only the top part is really what matters. This top part has to equal 0. This top part has to equal 0. And so now, like we did with sine and cosine, we're going to do some factoring. I'm going to factor out the 6 and the x. So I'm going to get 6x, x minus 4 equals 0. Okay, so now again I have my zero product property. 6x equals 0 and x minus 4 equals 0. So I've got x equals 0 and x equals 4. Amazing. Critical values. So little tips and tricks for solving. Are we missing anything? We got 0 and 4. First of all, let's check to see if those are in our range. Our range here is from -1 to +5. 0 is in that range and 4 is in that range. Yes, we're good. Is it in -1 to 5? Yes and yes. So we're good with those two. Are we missing anything else? Missing anything else? Oh, buddy. Something is missing. We have another critical value that we're missing. What's that other critical value that we're missing? The interval is from -1 to 5. Pariso says 2. Where does that number come from, Pariso? Why is 2 a critical value? It's not part of my answer here. 2 isn't part of my answer here. Why is 2 a critical value? G prime of 2 What do you mean G? I don't understand. G prime of 2. What is that? What are you telling me? Why is 2 a critical value? Very good, exactly, yes. When we had our derivative here, when we solved our derivative, when we cross-multiplied like this, we kind of erased this denominator, right? But we can't really erase the denominator. We have to include it as part of the equation. So we get rid of it and we find the two critical values without it. But to include it, we also have to imagine the derivative not existing. Okay, yes. Thank you, Haley and Jessica got it. Yes, sorry. I was looking at the wrong question. Hold on. The interval is not -1 to 5. It is -2 to 1. -2 to 1. Apologies for that. You are correct. I was looking at the wrong question. -2 to 1. So in that situation, -2 to 1. 0 is okay, but 4 is not. Outside the range, so the only one we care about is the 0. So we're going to ignore that 4. Very, very good. All right, so then again, same thing here. I'm going to find out where the derivative does not exist. And the derivative does not exist when the denominator, where's blue? Denominator here equals 0. When my denominator equals 0, this is a DNE. So x minus 2 squared equals 0. Well, here x equals 2 would be my my does not exist number. So that's another critical value where the derivative does not exist. Here's where the derivative equals 0, and this is where the derivative does not exist. But again, we got to check our range. Is -2 to 1, is that in the possibilities? 2 is outside that possibility, so we don't need to worry about that as well. So the only critical value we care about is 0. And of course the endpoints. 2 doesn't work, 4 doesn't work, 0 is the only one that matters. Oh, I ran out of room. Even though it's an important number, right? It's a place where the denominator does not exist. It's not in our range, so it's not part of our check. So now we're gonna set up our table, find our left point, right point, and the critical value. So I've got my left, x equals -2, my critical value, x equals 0, and the right side, x equals 1. Setting up my table here as I'm out of room. And let's plug it into our original function, f of x. Well, I guess it's g, isn't it? G, whatever. G of x, fine. G of x. Our original function was g of x was equal to 6x squared over x minus 2. So if I plug in -2, -2 squared is 4, 6 and 4 is 24, divided by 4. 6 times -2 squared over -2 minus 2, that's going to be 6 times 4 over -4, that's going to be -6. For 0, I've got 0 over -2, which is 0. And for 1, I've got 6 over -2, which is -3. So here's my max, and this side is the min. So there's our function, our maximum at 0, our minimum at -2. Okay, everybody? 0 on the top there. 6 times 0 squared is 0. 0 minus 2. All right. Great. Got something different, Parry? So what did we get? -2. Oh, wait. This would be 1 minus 2, right? Hold on, everybody. -1 minus 2, that would be -1, 6 over -1, which is -6. So I guess, yeah, both these are mins, wouldn't they be? Yeah. So what happens when I distracted by a yelling baby? So 2 mins and 1 max. All right, that's fine. So the graph is going to look something like, we know is going to look something like at -6, it's going to be -2 and 1. It'll be here, and it'll be here, and it's going to be 0, 0. So it looks something like it goes up, peaks out there, and comes back down to here. Something like that is what the graph is going to look like. I don't know exactly the curve, how the shape is, but I know it has to be going all the way up here, has to max out right here, has to come back down. There's nothing higher, no point is higher than 0. 0 is the maximum on this range. Nothing is higher than that value. Guaranteed because of our extreme value theorem. Because the function is continuous on the interval from -2 to 1, continuous on that interval. And because we found the max, we found our critical values. These are the only critical values in the range. So we know that has to be the maximum. There's nothing that goes higher than that point. Because if it did, we'd have a peak where we'd come back down and we'd get a 0 for a derivative. But this is the only place where the derivative is 0 at 0. Within this range anyway. So we go to -6 up to here, down to here, -6 at 1. Something like that is what the graph looks like. So we can get a lot of information, right? We're getting a lot of information from understanding our situational awareness of our derivative, what our situation is, what our endpoints are, we can know about the shape of the graph from this sort of gathering about the graph without having to plug in all these, like make a table of values like we did back in Algebra 1. We don't need to make this table. We have more subtle information about the graph. We know the max and min of the graph. We know the shape of the graph, how it's going to generally look. We know this 0 has to be the highest point of the graph. And we know these values are at -6. We know this is a 0. So we know it's going to look something like this. With these few points, we can extrapolate this idea of what the graph looks like. And this is what we're going to continue with, clearly not this time, but next time, when we talk about the mean value theorem and other things using derivatives to determine this kind of information. So I guess that's going to be it for today. We do not have time for me to start that next thing. It's too much. So get this homework into me. We went over these. Let's see. Can I do 37? No, I don't think I have time. Figure out 37. 33 with the absolute value. That's a tricky one. Absolute value derivatives are really annoying. I don't like them. So that's why I said extra credit. If you want to do it, have fun. But we're not going to do it here. But that is it. We're going to call it here. What I want to do this week, everybody, I do also, let's see. Today's Tuesday. Would it be helpful to have another study session on Wednesday to go over this or anything else that people want to go over? Or maybe we'll wait till Friday after the homework I give you on Thursday. What do you think, folks?